We're going to use our laws of logs now to solve equations. I mean, this is really what we've been building up to. This is the simplest equation that you might be asked to solve. What makes it different is the unknown is an index, and we sometimes call that an indicial equation. We have an unknown index. Whenever you've got an equation with an unknown index, then that is absolutely ripe for using logs to solve. And as a matter of course, when you see an index, an unknown index, you're always going to be thinking, I need to take logs. So you've just got to remember this is how you do it. You take logs of both sides. It doesn't matter what the base of the log is actually. Now I'm going to do base 10 to start with. And then I'll use a different base just to show you that it doesn't actually matter. So all I've done, we've followed the rules of algebra. What I do to one side, I do to the other. I've taken logs of the left, the whole of the left. I take the log, the whole of the right. It's the same base, so I've done exactly the same thing. And the reason why I've done this, the whole point of me taking logs was now I can exploit the third law of logs to bring this index down. So I've basically brought it into a position I can now deal with. And there we have an equation. Log 3 has a value. Log 20 has a value. They're constants. But what I'm going to do is divide both sides by log 3. And now we can just put this into the calculator and it will give us the answer. You may be able to see what the trap here is. There are some people who mistakenly try to use the second law of logs and do something silly like change this to log, just one log, log 20 divided by 3. So again, I'm just bringing this to your attention just to show you that this is the most common error, if you're going to make an error at this point, that people do. That can definitely not be done. It's when we subtract logs that we would be able to do this. So this would be okay if I was doing this. But you definitely can't use the laws of logs here. And why would you anyway? Because this is just simply something that you can just put straight into the calculator. And what you'll find is three significant figures, 2.73. Now, I'm going to start again. And I'm still going to take logs. So I'll write the initial equation down. But I'm going to take natural logs. Because in some specifications, this is always the preferred base to use. But nothing special about it other than it being a particular base. I still use the third law of logs to bring this x down. And again, this is a constant. You could put natural log 3 in your calculator, get an answer, and the same here. So I'm just going to divide both sides by log 3. And again, I'll just get different values. So I'm just going to do this to a few decimal places. I'm not going to mess around. And then if I evaluate that, I get exactly the same answer to three significant figures. So the point I'm making is, with an equation like this, doesn't matter what logs you take. Now remember, you're doing the same to the whole of the left and the whole of the right. Don't break the rules of algebra if the equation doesn't look like this and you can't do that. You'll see anyway as we go on what I mean by that. Again, here we have an indicial equation. We've got unknowns in the index. Again, the minute you see an unknown in an index, you know that's ripe for taking logs. So I'm going to do the same to the whole of the left and the whole of the right. And I'll use natural logs here because I know that's preferred in some specifications. And the whole purpose of me doing that, the reason I did this was because I knew I can now exploit the third law of logs. And remember, I'm bringing the whole thing down. Okay, so again, remember these are just constants that we've got here. Some people are sort of, think, well, what do I do here? But stick with what you know. This is a constant. This is a constant. So if, for instance, I was ever to write out you'd probably have no problem at this point. You'd think to yourself, well, I expand the brackets. In algebra, there's rarely just one way to do things. But when you see brackets, frequently the best thing to do is just to multiply them out and see what happens. And again now, you're very familiar with this. It's an equation. We've got x's on both sides, so we want the x's to be on one side. So I'll subtract x log 3 from both sides. And I'm also going to subtract log 7 from both sides. Now I know I'm going against advice I've given in the past in terms of step by step. So you don't jump steps in tests, but I'm doing it just for the speed of the video. I'm going to take out the common factor of x. And then whilst these expressions might look complicated, this is just a constant. You could type this into your calculator and get a value. You could type this into your calculator and get a value. And so you can see what's coming. And again, I'd suggest that you do this yourself. So don't take my word for it. But there we have the answer to 4 significant figures. Again, in a test, you don't need to wait for this to be marked, to be sent off, to come back. You substitute in, and the left should equal the right, and you will know for sure whether you've got this answer correct or not. This is another form of equation you might solve. You've got to get used to just recognizing this, that it's a quadratic in disguise. It's got that telltale, sort of format often. I mean, I could sort of rearrange it to try to throw you off, of course. What it comes down to, the trick is, and it is a sort of a trick in a way, look at the middle term, which would be the x term, and this is always going to be the giveaway of what the substitution is. So for instance, if you make y equal 5 to the power of x, you can only make one substitution. There's only one thing that works here. So you would end up with 5 to the power of 2x plus 7y minus 30 equals 0. That's not good enough. because you've still got this. And what this relies on you spotting is what happens if I square y. So I'm squaring y. In turn, I'm going to square this. And remember, I'm squaring the whole of this. And then this, of course, should remind you of the rule of indices, that when I'm taking this, in turn, I'm taking a power, then I multiply these two together. So I will end up with 5 to the power 2x. And then you see that as well as your original substitution here, y, you also find that y squared is just what you needed to make the substitution there. The reason is these questions will be contrived so that that is the case, because otherwise it just wouldn't work as a quadratic. And the insider tip is look at the middle term. This will, invariably give you the substitution that you should be using. And then this allows me to make the straightforward substitutions. Y squared plus 7y minus 30 equals 0. Now I'm not going to waste my time solving this. You can do this. I'm just going to write down the answers. Y equals minus 10 or y equals 3. And then, like all of these questions, we just look back to our original substitution. So we end up with these two equations that you then solve. And again, we ask ourselves, how do we solve these? Just as we've done in our first example, we take logs of both sides so that we can exploit the third law of logs. Now, it may be the case that just as if you've got experience with using substitutions to solve trigonometric equations, there may be no solutions. So both of these, you may be able to solve, or perhaps just one of them you can solve. So you can see what's really I'm leading to. If I try to take logs, so this time, all right, I'll just take a normal log. At this point, hopefully you've got enough knowledge to realise that you can't have a negative log like this, because what you're saying, what is the index to the base 10 that results in the value of minus 10, and it doesn't exist. So you know that there's no point in proceeding with this. This has no solution. If now you need to be sure of that, and if you're not sure, you need to ask yourself why you're not sure and find out why. But if I was to draw the graph of y equals 10x, there is no power that I can choose that will give me a value of minus 10, because all it does, as we go towards a negative very large number, we approach 0, and as we go this way we approach a huge number, but at no point can we select a power that gives me a negative number. And we do just the same here, take logs. To allow us to exploit the third law of logs. These are constants, and you know what to do from here.